The following program has been made possible by financial support from the American Chemical Society.
Welcome to Science in the Written Word. I'm Lou Massa. Today we have with us Professor Ronald Breslow, the author of a book called Chemistry Today and Tomorrow. It's published by the American Chemical Society and Jones and Bartlett Publishers. Dr. Breslow is professor of chemistry at Columbia University. He's the immediate past president of the ACS. A distinguished researcher, he's the recipient of the National Medal of Science. I think that was awarded by
George Bush
in 1991.
That's right. That's right.
Welcome, Ron.
Thanks very much.
Maybe we could begin with something of the general idea of what chemistry is. And I wonder if you could just read from the first page of your book.
Sure. Yeah, I'll read from the beginning of chapter 1. This is a very common thing that book authors do. We love our own words. Let me read first I always have little quotes at the front of every chapter. The chapters are constructed so that most of the chapter is about where we are right now. There's always a future section at the end, where we're going, which I think is of a lot of interest to students. And there's always a quote at the beginning. The quote at the beginning captures very well the spirit of chemistry. It's a quote actually from George Bernard Shaw, though a lot of people think that Bobby Kennedy invented it, but Shaw wrote this. He says, "You see things as you are, and you see things and you say why. But I dream things that never were, and I say why not." And that actually very much captures the spirit of chemistry. Chemistry, let me read now from what I say here. Chemistry is a science that tries to understand the properties of substances and the changes that substances undergo. It's concerned with substances that occur naturally, the minerals of the earth, the gases of the air, the water and the salts of the seas, the chemicals found in living creatures, and also with new substances created by humans. It's concerned with natural changes, the burning of a tree that's struck by lightning, or the chemical changes that are central to life, but also with new transformations invented and created by chemists. And the point of the quote is that chemistry does both of those things. We try to understand the world as it is, but we also create a whole new world of chemistry that's consistent with natural law, but that actually sort of extends what nature has provided.
Yes. Now, certain fields of study are thought of as very ancient. Astronomy typically is. And you can imagine the first people, that is to say very ancient people, walking out and being attracted by the stars and so on. But as regards chemistry, should we imagine this as well as quite an ancient science?
It's extremely ancient. When you think of what chemistry is, it is essentially, much of it is transforming something into something else.
Right.
So go back to earliest times in the cave, where people, by heating wood, turned it into charcoal. That's a chemical process. It's actually a process we still run today. And it's not just, you're not just heating water to evaporate it, you're actually changing the composition of the wood into something different. Or actually the manufacture of soap, that goes back to pre-recorded times. Because when fats dropped onto the ashes of wood fires, there was a chemical reaction that turned the fats into soap. And we don't use wood fires anymore, but it's pretty much the same process. And even some of the things that most people would understand as chemical manufacturing, like the manufacturing of glass, goes back, thousands of years BC.
So it is an ancient science.
It's an ancient science, and so in that sense, it's almost a problem for us, because it's so ancient, it's so pervasive of our society that people take it for granted, and they also, are always looking for the new face on the block. And so the question is chemistry the new face? And of course, much of it isn't. I mean, we're still making soap, and as they started way back, we're still making glass. Right. But in addition to that, there's a lot of new stuff that's going on in chemistry. It's very exciting.
What about back at the very beginnings of civilization as we know it? Wouldn't metals have been an important product?
Sure, and you think of it. Most people think of metals as, well, here they are, but in fact metals are manufactured by a chemical process. There are only a few metals that occur as real metals, natural. Gold, platinum, and a few things of that sort. Most metals we think of, like iron, copper, steel, these are made by a process which is really pretty amazing. When you think that people had no idea what they were going to achieve, they took some dirt out of the ground, which happened to be iron ore, mixed it up with charcoal and heated it, and produced this wonderful material, iron. And that one didn't have that before. I mean, it's a created product. And essentially
So
every metal.
The metals don't come naturally. They're found as ores, and somehow you have to separate the metal from the ore.
Yeah, and you have to perform a chemical reaction to do it. And that's the part that's really astonishing, because how did people know this? They really didn't.
It must have been accidental, eh?
Yeah, but it was accidental in a very interesting way. I mean, people started mixing things up and heating them to see what happened. And we actually still do some of that today. It's not the only thing we do. But it was a very interesting and creative idea. I mean, who was the person who dreamed up mixing sand with a few things and heating it up and turning it into glass? You know, all of this stuff happened by just curiosity. People discovered if they heated mixtures up, interesting things sometimes happened.
Right.
And that's what the alchemists did. They heated things, everything in the world together to try to make gold. It didn't work, but it was an interesting idea.
Right. Was making gold the driving idea of alchemy? Was that the whole point?
It was the thing they certainly talked about, and I think they all realized if they could turn something cheap into gold that they could retire in the style that they would like to be accustomed to. But in fact, the contribution of alchemy was terrific, because in the course
How
of
so? What has come down to us?
Well, in the course of them trying to do this, they mixed up everything in the world and heated it up. So a lot of the things that we now take for granted were discovered by that same business of heating things up together. An awful lot of ores, of materials you can find in the ground that, you know, we call it iron ore because we now know it has iron in it, but when you look at it, it doesn't look like iron, it looks like clay. Awful lot of that stuff, when just mixed up with charcoal and heated, produced very interesting things. All the metals were discovered that way.
Yes.
And in fact, we almost make iron the same way now. Luckily, we don't use charcoal anymore. It was eventually discovered you could use coke, which is sort of coal that's been heated a bit. And it's a good thing, because it's been estimated that during the industrial age in England, if they had continued to use charcoal, there'd be no trees left in England.
Yes.
I mean, there's just too much.
You have a wonderful picture of an alchemist in his rather primitive laboratory, and the furnace is an obvious thing, and the bellows and so forth.
That's right.
So
Yeah.
that was one of the major driving forces that was used then and is used today to drive chemical reactions.
Well, there's still a certain amount of what chemists call shake and bake. You know, we do this because we're a little ashamed of that style of chemistry. We do some of that, but now actually it's done in a very interesting way. First of all, we have a much better idea what's going to happen when things are allowed to react. Usually it takes heat to make things react, but not always. So we usually have a better idea. And secondly, in exploration, say for new pharmaceuticals, new medicines, which chemists do, that's fairly common still to sort of do a certain amount of let's try to see what happens and see whether these compounds have interesting activity. An awful lot is done of so-called rational drug design, but you know, sometimes you think you're designing a rational drug for cancer and you discover a wonderful drug for something else, you know, so you don't always know ahead of time.
Yeah. The alchemists, would they have been responsible for inventing much of the glassware and the experimental pieces of equipment that are found actually in modern-day laboratories? Well,
they certainly gave it a start. I mean, the wonderful glassware that you see in exhibits of old alchemical laboratories, you know, we can all identify with them. They sort of touch a basic chord, but we don't use those exact structures anymore. Modern chemical glassware,
they're more or less suggestive of the
Yeah,
modern
they
stuff.
suggest it. I mean, they used to make a single piece. We now make pieces that can be fit together in various combinations, so it's a somewhat different style.
Well, alchemy came to an end at a certain point. When would that have been, in rough terms? And what would have marked the change from the shake and bake, very empirical notion of trying to make gold onto the modern ideas of chemistry?
Well,
where does that happen?
I think what happened is that increasingly people had an idea of what was going on, and it wasn't a total mystery when you mix things up. New techniques were developed whereby people could figure out what was in the things they were pulling out of the world, and new theories developed whereby people could begin to predict what would happen. And much of this happened. Actually, I mean, it went on for a while, but there was a sort of a great birth in the 19th century. So chemistry is really, you know, quite an old field in that sense, and chemical theory is quite old. I mean, we still have journals that we go back to that have things that are useful for modern chemistry that were written in the late 18th century even, and certainly in the 19th century.
Yes.
Very active, as well as, of course, exciting things now. I mean, there's a tremendous burst of activity in chemistry as there is in most scientific fields.
Yeah.
So there's a huge amount going on now, but still, some of the early stuff is quite relevant.
There was a time in the 1700s where chemists, for some reason, began to emphasize the importance of quantitative measurements. At the time of Boyle and Lavoisier, and somewhat later Dalton and so on. And it seems to me that might have given birth to what we might call now modern chemistry.
Yeah, well, modern chemistry has branched off a bit now. There are a lot of different things. There's a very quantitative part of it. There's a theoretical chemistry. There's a computational part of chemistry, which is very, very active. Many people are doing computer modeling, essentially, of chemical reactions. They're trying to predict what will happen in an unknown case, what will the properties be of an unknown compound. Can one design a new medicine to fit a particular receptor? And so a lot of people who are very excited about using computers, a lot of young students, for instance, who are very interested in computers, find that this is an excellent place to go because computational chemistry is an absolutely growing section of our field.
Yes.
And there are jobs. Every drug company has a computational chemistry section, for instance, trying to design medicines using computers.
Yeah. That's an important point. Students often don't realize that there are jobs out there in certain areas, and this computational chemistry is an important field where there really are jobs. Can you speak a bit to what some of the fundamental ideas are which underlie modern chemistry? Without going into elaborate detail, because obviously no one can in 30 minutes. But what are the big ideas, maybe, that one could mention?
Yeah, I mean, I summarized them in the book to some extent, and I try to do that carefully. But they fundamentally involve the idea that the properties of compounds depend on what's in them and how they're arranged. And the arrangement is important.
Now, what's in them? Are we speaking about the atomic structure?
Yeah, well, we're speaking about the elements. For instance, let me give you an example. If you have 2 carbons, 6 hydrogens, and an oxygen in a molecule, and we can determine that with various instrumental methods, that, as it turns out, helps to define the molecule, but it doesn't define it completely. It also depends on how things are connected. So that, for instance, if all 6 hydrogens are sitting on the 2 carbons, 3 on each one, and an oxygen in the middle, we have a material that's an ether called dimethyl ether, and it's related to the ether we use in anesthesia. On the other hand, if you have 3 hydrogens on one carbon, 2 on another, and 1 hydrogen on the oxygen, then you have a material, ethyl alcohol, which is in fact the alcohol that's in beverages. It's the alcohol that's in beer and wine, that sort of thing.
So it's the same atoms, they're
connected differently.
We have isomers.
That's right. And so part of chemistry is figuring out how things are connected. Part of chemistry is figuring out how to make them connect right. That is, you want to make a molecule. You can't just mix these all up and hope it happens. You try to put them together. It's like putting together a building. All these buildings are built of the same bricks, but how you arrange the bricks depends on what building you end up with.
There's also a very subtle sort of isomerism that you mentioned, the chiral isomers.
Yeah, it's the right and left-hand thing, and I think a lot of students hear about this, and it's very important. It turns out that drugs, medicines, generally are active if they only have one particular handedness. So, for instance, my right hand and my left hand are obviously not identical, and if I had say a fielder's glove, I happen to be left-handed, so my fielder's glove fits here and it doesn't fit over there. And the same thing with shoes. Your shoes will fit your one foot and not the other.
Is this important?
Oh, it's terribly important because all biological molecules, with almost no exceptions, come as one of the kinds of handedness. For instance, every enzyme, every protein is made up of amino acids which look like, let's say, my right hand but not like my left hand. And so something that's going to fit, a drug that wants to fit in there, has to be like a right-hand glove, not like a left-hand glove.
Right.
So it's absolutely critical that we, first of all, understand it and secondly, design it correctly.
Actually, one of the interesting fundamental problems out there is the question of why amino acids, for example, are right-handed. It's not particularly understood.
No, it's not understood.
I think I read an article in the New York Times about a week ago, maybe 2 weeks ago, to the effect that they examined the amino acids from a meteorite from outer space and found that there was a predominance of one-handedness over the other. And so the interest is whether such experimentation could lead to an explanation, for why one chirality versus the other.
Well, it's an interesting point because, as it turns out, if you do a chemical reaction with something that doesn't yet know whether it's right or left-handed, let's say you have a piece of leather, you haven't yet carved a shoe in one shape or the other, then the question is which shape will that piece of leather turn out to be? And of course it could be either one. And in fact, obviously you make both shoes out of the same kind of leather. And that's also true of molecules. Some molecules can be turned into either right or left-handed molecules. And so the question is, where did that all start? Now, what people are saying in that case is, well, maybe it came from outer space, and it's an interesting question, but it just pushes the question off, because how did it happen there? but I think increasingly we understand it. It turns out that a very small advantage of one over another, maybe even an accidental advantage, can get multiplied. There's a process called catalysis in which molecules can induce the formation of other things. So a small amount of a right-handed catalyst somewhere can produce a lot of things that are essentially right-handed in character.
Yeah, that's interesting. But more on the fundamentals of chemistry, what about reactions and reaction rates? What are the big ideas that determine whether, when you mix things together, the reaction goes yes or no?
Yeah. Well, there are two things that matter. One is, will it be favorable? I mean, it's very much like a common human experience. I mean, you can roll downhill, you can't roll uphill. You have to work to roll uphill. So if you wanted to run a reaction that was of that made a high energy product, you'd have to supply that energy somehow. But otherwise, you could just coast down. But for instance, I mean, one of the analogies which I like a lot, because it just happens to work nicely, is that the city of Denver is one mile-high city. You know, they talk about it. And on the other hand, San Francisco is down at sea level. So what does it take to go from Denver to San Francisco? Well, you think you could just coast downhill. But the problem is there are mountains in the middle, and you've got to go over those mountains.
Right.
Well, it's the same thing in chemistry. It may be a downhill reaction, so it may be favorable. You could coast, except you have to supply some extra energy to get over those mountains. And that's why you have to heat most reactions, because even if they're favorable, you need some extra energy to get over that sort of energy mountain that lies between the starting material and the products. And one of the interesting things that catalysts do is they figure out, or they don't figure out, catalysts do, I guess I don't want to make them too personal here, catalysts achieve a process of essentially solving that mountain problem. The way we solve it physically is we dig a tunnel through the mountain so that there's another pathway that's not, you don't have to supply so much energy, you know, dig a railroad tunnel right through it. What the catalyst does is to make a new pathway for the thing that can go through and avoid that mountain, and therefore makes the reaction go fast.
There's also this additional factor of entropy, this famous word, that also enters whether or not a reaction will go forward spontaneously.
That's right. And that's an interesting thing. You know, it's a concept that is, it sounds peculiar, but it's a very common experience. If you take a new deck of cards and you open it up and they're all nicely ordered, you can start shuffling them, and they will immediately disorder, and no matter how long you shuffle, they will never come back to the original arrangement.
Right.
The original arrangement has a lot of order, everything arranged exactly so, and the spontaneous direction in the world is for things to move from order to disorder. That certainly happens in our government, let's say, in politics in general.
And it happens with chemistry as well.
It happens with chemistry.
Yeah.
The things goes to a more disordered state. So when I say you have to go downhill in energy, there also is a disorder part to it. Both are there.
Yeah.
You know.
Let's talk more particularly about life for a while, the chemistry of life. Has chemistry contributed much to our, in fact, knowledge of what the nature of life is?
Huge amount. In fact, what we generally do when we explain something, you know, what do we mean by explain something? We put it in terms of something else that we think we understand better. The living process is fundamentally a chemical process. That is, food is brought in, things that it's transformed into other things, energy is generated, even motion of muscles, even the thing I'm doing right now with my hands, all of that is essentially a chemical reaction that is making my hand able to close. And we increasingly understand that. Much of that is done in a subsection of chemistry called biochemistry, the chemistry of life. But there are other parts of it. There's a section called bioorganic chemistry, biophysical chemistry, even molecular biology, which is heavily focused on the chemistry of nucleic acids. But the people who do this generally we identify them as chemists. I think they are chemists. They certainly have huge amounts of chemical training. And so one of the leading biologists, Nobel Prize winner in biology recently, said that as far as he was concerned, we will understand life when we can put it all in chemical terms. And I think that's correct.
Mm-hmm. Tell me more about molecular biology then. I mean, what is the field? What's it about? What do they want to look at and learn?
Well, you see, one of the very exciting things, of course, about life is that it comes with this set of instructions. You know, in other words, things don't just happen at random. So one has DNA, which carries a code, and but much of which is still actually not well understood. It turns out, for instance, the DNA that we have has lots of sections that code for particular proteins. Many of them are enzymes, which are catalysts that we need for life. But then that's only about 10% of the DNA. About 90% of the DNA has a function that we don't understand yet. It's in there, people have various ideas about what it does. Some of these ideas actually are founded on some reasonable kinds of evidence. But still, only about 10% of the DNA carries the code letters that we understand as being important for specifying the molecules of life. So molecular biology wants to understand the whole thing. They want to understand how this all occurs. They want to understand what's going on there. But also, they are in the same kind of business I mentioned before. That is, they are not just saying, isn't that interesting, let's admire it. They are also saying, what else can we do? So that they, for instance, are doing what's called mutations to change the gene, to change proteins, maybe make them more effective. If you want to catalyze reactions using a protein, it might be very important that that protein be heat stable, so you could actually run the reaction at high temperature instead of normal room temperature. And so people change the genes in order to do that. So they're doing the same sort of thing that I mentioned earlier. They're first of all looking at nature, and that's an important thing that all scientists do. But in addition to that, they're messing with nature.
Yeah.
They're expanding on it.
Yeah.
And it's very different, you know, from other sciences. When you think of it, I mean, we have a section of chemistry called synthesis, where we make new molecules. I mean, about 95% of all known chemical substances are substances that people made, not substances we found in nature. And in 1995, I think something like 1 million new chemical substances were registered in one of our things called chemical abstracts, where we register things like that. But, you know, other fields don't do this. I mean, the field of sometimes I talk about this to audiences. The field of synthetic astronomy is a virgin field waiting to be done, you know. Where are the people making different universes to see how they compare with the one we have? You know, nobody does stuff like that.
Yeah.
That's what chemists do.
Yeah.
We make different molecules to see how do they compare with what nature supplied. You know?
I actually have heard of people who have conceived of creating a new Big Bang, actually.
Oh.
Or perhaps a small Big Bang.
Yeah.
But
Yeah, the technical challenge is fairly substantial.
exactly. Now, you've told us a little bit about catalysts. I mean, these are molecules that serve the function of speeding up a particular chemical
Right.
reaction. It's that process you described in terms of getting over an energy mountain by
finding a new pathway.
either going through or around,
get around or
a
something.
new
right.
pathway. Right.
Sure.
Now, the archetype great catalyst in the chemistry of life would be these big proteins that are
Right.
called enzymes,
Right.
the technical word. What about these enzymes?
Well, they are, much of biochemistry is focused on enzymes, trying to understand them. There are two things that people try to do. They try to figure out which enzymes are involved in any particular process, and then try to figure out how they work. And some of that also
How
involves...
many enzymes might there be in the life process?
Oh,
Are we
gee.
talking about a finite number that we can get our mind around?
Yeah, it is. I have the number in the book, and I don't remember the number. It's in the thousands somewhere, and the number I remember is 5,000, but I
So
think
it's actually a very small number.
It's a finite number that people have found so far,
Right.
although people keep finding new things, so one has to be careful about putting a limit. But it's not millions, you know.
Right.
And many of these have been, the structures have been determined. That is, the three-dimensional arrangement of all the atoms, so exactly what the shape is. Many of these have now been determined by techniques, modern techniques called X-ray crystallography and some other techniques, so-called nuclear magnetic resonance. These are techniques that chemists use that are very close to physics, actually. They, you know, because chemistry ranges all the way from almost physics to almost biology.
Right. And there's a one-to-one correspondence between the code in the DNA structures that we talked about earlier and the proteins that,
That's right,
that
exactly
follow
right.
from that code.
Exactly right. And but you know, there'll be many. Actually, in fact, it's quite interesting. The organization. We don't want to go too much of this probably, but the organization is quite interesting. You might have a whole bunch of genes clustered together that specify a whole set of enzymes that are all involved in a single process. For instance, there's a snail that lays eggs, and it needs a certain number of proteins in order to specify how it behaves and how it does it. And the genes for all those are actually clumped all together. So there's a whole section of DNA that says, here's how this snail shall lay an egg. You know, so it really is
Yes.
quite remarkable.
How fast are these enzymes, and how selective are they? And, is that important?
Oh, yeah. Yeah, see, speed is important. I think I put the numbers down, something like many enzymes will give you a 10 to the 12th, that's a 1 with, you know, with 12 zeros after it, you know. A 10 to the 12th acceleration, a huge acceleration. And so I pointed out that, for instance, if you didn't have that kind of speed, life would be completely impossible. I think the number I gave is that if you just read that last sentence in 5 seconds, it would have taken you 100 years or something or other to do it without the enzymes. Of course,
Yes.
it's totally impossible. So the speed is critical, but the selectivity is also critical. The enzyme has a particular shape, and some molecules fit in it and others don't. And so it's able to operate in this great sea of things that we have in our cells. You know, you know, many, many hundreds of compounds in there floating around. The enzyme can bind a particular one to it and carry out a particular reaction to it, and that's critical. And so that they're both things that we're trying to learn to imitate in chemistry that trying to extend biology, essentially.
Yeah. Actually, how much do we know about the enzymes and the way they work?
We know a lot in the sense that we know we can see what they look like, we know where the groups are, we know pretty much which chemical groups are doing what in many cases, but there's a missing part of it somehow. We can't really say yet, this is the part that's important, that part is there, but it's not so important. And that's part of the reason we extend nature. I mean, one of the things that we do with an extension of nature is to try to understand not only what's out there, but why it's there. What is its function, you know? How important is it that a particular vitamin has that exact structure as compared to some different structure?
Yeah. Have you ever heard of mimetic chemistry?
Yeah, biomimetic, yeah,
Yeah.
right, yeah.
And
Yeah, this is the phrase, this is a word I invented, so I certainly heard of it, yeah. Yeah, it's partly what we do. We, you know, we're trying to mimic biological chemistry. And, you know,
But what I'm getting at is for what purpose?
Two purposes. For one thing, you have to admire what's going on out there. I mean, as I say, nature is giving reactions that are speeded up by 10 to the 12th, huge accelerations. We aren't able to do that yet, and it would be very, very useful to do it. Nature does wonderfully selective chemistry. In the making of cholesterol, for instance, which is an important compound. I mean, you don't want to have too much of it. You've got to have some, otherwise you're not going to survive either. I mean, the making of cholesterol, nature is able to, with an enzyme, is able to bind a molecule and go in and carry out a reaction that is just very selective for a particular part of the molecule, and we don't know how to do that yet. So it would be very useful for us to know how to do it, but in addition to that, we'd also like to understand how nature does it. So, you know, again, it's both parts, understanding and also extending or applying.
Chemistry is such a vast subject. We've barely scratched the surface. We're coming to within a minute or so of being out of time.
Sure.
Could you just look at page 119 where we have a kind of summary remark that you might read for us?
Page 119. Okay, here it is. Yeah. All right. Here's my postscript, because it's really addressed to students. This book, I hope, will touch them, because in it I talk a lot about what's left to be done. So I say, in this book I've tried to give the reader some idea of the great range of chemistry and its importance. In common with other scientists, chemists explore the natural world and try to understand it. However, chemists also expand the world, creating new chemicals and inventing new chemical reactions. There are many important questions waiting to be answered and many practical goals that will permit chemistry to contribute even further to human welfare. Students considering chemistry as a career have a choice of creating new medicines or making other contributions to human health, devising new materials with important applications, helping to improve the environment, an important part of chemistry, by the way, helping to advance the computer revolution, helping to elucidate the fundamental chemistry of life, or helping to understand the fundamentals of chemistry itself. It is an important challenge. I hope that some readers will be inspired to take up the challenge and make their own contributions to the science that is uniquely central, useful, and creative.
Thank you so much.
Thanks, Lou.
Yep.
Yeah.